Hi everyone. Today we are going to continue our discussion about the binary search tree. And since it's a new topic, let me spend a little more time to do a review. Okay, for the binary search tree, and this is the structure that we want to organize the data using the concept of a key and then associated satellite data. Okay, and why do we want to have a key? And we want to have a key to do the fast searches. And you can consider a key as a unique identifier like our social security number or our student ID. Okay, and then for each of the nodes we have in the tree, and then we have a key which is the unique identifier. And after that, we also have two cursors or two pointers to the left children and then the left child and the right child. And then we also have a P, which is for the parent. So that pointer will refer us back to the parent of the current node. Okay, and then for the binary search tree, there is a very important property that is for the key on the left subtree, and it should be smaller or equal to the key of the current node, and then the key of the current node should be smaller or equal to the key on the right subtree. Okay, and then this rule should be true for all the parent and the children pairs. Okay, well, and then if we enforce all the rules, and then we have a valid binary search tree. And by the way, even if we enforce this rule, and we can have a binary search tree, but it doesn't really mean that this is an ideal binary search tree. And later, when we're talking about the efficiency of the queries or the height of the tree, and we will see more about this. And then we talk about the tree walk. And for the tree walk, there are three different ways. And the pseudocode we are seeing here, that is called the in-order tree walk. And for the in-order tree walk, for each time when we visit a tree or a subtree, we want to finish doing the traversal or the tree walk on the left subtree first before we do the root, and then after we touch the root, and then we move on to the right subtree. Okay, so this is called the in-order tree walk because we touch the root or we visit the root in the middle. Okay, and then if we want to put this line of the code to touch the root at the very beginning, and then we have the pre-order tree walk. And another way is if you put this line to which is to touch the root of the tree at the very end, and which is at here, and then you have the post-order tree walk. Okay, so there are three ways to the tree walk or traversals. And for example, if we want to do a in-order tree walk, and then you will find something really interesting, because the sequence of doing the in-order tree walk for this tree will be you start from the A, and then after that B and D. Okay, and after that, all the left subtree is done. B will visit F, and after F we visit H, and then we visit K. So what's the interesting part here? Well, when we are doing the in-order tree walk using a valid binary search tree, and then we are visiting all the keys from the lowest to highest. And what does that mean? It seems that we are going to have all the values sorted. Is that correct? And later we're going to talk about this. Okay, and then how long will this tree walk take? And then we will say this is theta n. So if n is the number of the nodes we have in this binary search tree, and then we just visit each node once and only once, right? So how long it takes is really linear to how many tree nodes do we have. Okay, and then for the binary search tree, another thing we want to do is we can do a search. Well, say if you have a tree, and then if you have a key you are looking for, and then you want to make use of the binary search tree property to do the search. And for example, if you're visiting a root, and then you want to compare the key you are searching for with the key on the root, and then depending on whether the key you are searching for is larger or smaller than the tree root, you only want to go one side of the subtree to continue your search. Okay, so let's say if we are looking for the D, and then we are comparing the D with the tree root, which is F. Okay, and then F is greater than D. And what does that mean? This means if we are going to continue do a search of the D, and if this D exists in this tree structure. It can only exist on the left subtree. So we go to the left side and then we continue the search. We want to compare the D with the B, and then okay, D is greater than B. So if there is a D and D should be on the right side of the B, so we go further down. And eventually you will either find the key you're looking for or you reach the end, which is a now, and this means there's no more nodes to go down. And then either way, you find the key, or you find the key you're looking for, or you find a now saying there's no such value. Okay, and then to do the search, there's another way without doing the recursion, and we can have an iteration version, and we have a discussion about which one is more efficient, the recursion version versus the iteration version. And the answer is, for the iteration version, it will be a little bit faster. Okay, and then we talk about the insertion, and for the insertion, you can consider it to be another search task. Excuse me. You can consider that as another search task. So instead of searching for whether we have such a key in the tree or not, now we have a key and we are making use of the binary search tree property again, but we are searching for a right open location for the new value. Okay, and then if you're trying to insert the C, and then we make a comparison, and then we say, okay, if we want to insert C, you have to insert to the left side of F. So we go to the left side, and then we compare C with B, and then we say, okay, C has to be inserted to the right side of the B, and then we go down, and then we compare C with D, and then we say, okay, C has to be inserted to the left side of the D, and then you will find that eventually on the left child of D is open, so we can insert the C here. Okay, and then for the running time, when we are doing the tree search or the tree insertion, and you will find that the running time is really linear to the height of the tree. Okay, and then it's in other words, whether a binary search tree is going to be efficient or not, it really depends on how high the tree is. And then if you even if you have a certain number of the nodes, and then depending on how the binary search tree is built, this binary search tree could be a kind of shorter tree, or the binary search tree could grow really tall. Okay, and then so what's the height of the binary search tree? And in the worst case, the binary search tree will be the height of the binary search tree will be O n, and in a good for a good binary search tree, and then the height could be O log n. So let me explain what's going on here. So let me go to my drawing board, and here I have already created a binary search tree. And as you can see, we have the 5, and then 2 smaller than 5, 8 is greater than 5, and 1 is smaller than 2, 4 is greater than 2, and then 6 is smaller than 8, and then 10 is greater than 8. So it seems that we have a reasonable binary search tree, right? And you may find this is also a complete tree structure. So is that a good news or a bad news? I would say this is good news. Why? Because the height is only 3, right? So for this tree, we have the height. Oh, come on. We have the height as a 3. So this is a nice binary search tree. Okay, and then what if we have a bad binary search tree? And what do I mean? And let's say instead of having 5 as a root, and how about we have 1 as a root? And then we have 2, and then we have 4, we have 5. Oh boy, and probably you can already see that this is bad, right? There's something wrong with my drawing board for some reason. Uh-oh. And then if we want to continue, we have 6, we have 8, and then we have 10. Okay, so if you compare those two binary search tree, what kind of problem do you see? So the number one thing, what's the height of the binary search tree on the right side. And you may say, hey, is that still a binary search tree? And the answer is yes. Well, it's just kind of unfortunate because this tree only grows on the other side. And then if you want to check the left child of 1, and then that will be a null, right? So, well, a null can still be having a null on one side, it doesn't hurt anything, and this is still a valid binary search tree. And the problem is, say, if on the right side, if you want to do a search, okay, and then how many comparisons do you have to do? And say if you're searching for 11, for example, and then 11 compare with 1, compare with 2, 4, 5, 6, and all the way down, right? So we have to do a total of 7 comparisons before we can say, there's no 11. So not so cool. Why? Because we do not make full use of the binary search tree property. In this search, we are searching for 11, but this search is as bad as a sequential search. So we use a binary search tree. Here, we use a data structure, but we are not making full use of the potential of the binary search tree. And we prefer the case on the left side. Say, if you're looking for 11, how many comparisons do we have to do? 1, and then we will go to the search on the right side, and another comparison on with 8, another comparison on 10, and then we will say, there's no 11, right? So that's the difference. To search for the value 11 on the left side, we have a total of 3 comparisons to do because the height is 3. And on the right side, we have a total of 7 comparisons to do, and the height is 7. Okay, for both cases, the cost of doing a search is OH, and this H is the height of the tree. And as you can see, we want to, if we have the same number of the nodes in the tree, we prefer to have a balanced, shorter tree, closer to a complete tree on the left side if possible. And we don't like the tree structure on the right side. This tree grows only on one side, or is highly imbalanced toward one side. And then for this type of the tree on the right side, it will make the searches less efficient. Okay, so this is the review part of the binary search tree, and then we will move on and to talk about how we can make use of the binary search tree to do sorting. Okay, we are coming back to sorting again. I will see you in the next video.